Welcome to The Explainer. Today, we're diving straight into a field that literally builds the modern world around us, chemical engineering. We're going to see exactly how we take abstract, theoretical chemistry and scale it way up to massive industrial production. It's the ultimate intersection of molecular science and real-world impact. Let's get into it. We've got a packed roadmap for this explainer. We'll start with molecules to global solutions, then walk through the infamous four-year curriculum. After that, we'll hit careers, salaries, and reality, look ahead to the AI and green future, and wrap up by asking, is this your path? So ask yourself, when you look at your smartphone, or life-saving medicines, or even just the fuel pumping into your car, who actually figured out how to manufacture all of that at an industrial scale? I mean, it's really easy to picture a chemist in a white lab coat holding a beaker, right? But honestly, a tiny lab reaction is a very long way from global distribution. Check out this staggering statistic. Over 96%. Chemical engineers are the ones designing the massive processes that produce over 96% of all manufactured goods globally. That is almost everything you touch. Whether it's the clean water you're drinking or the advanced composite materials holding an airplane together, a chemical engineer had to figure out how to make the process viable, completely safe, and most importantly, economical. So what actually is it? Well, chemical engineering is basically applying chemistry, physics, heavy math, and economics to efficiently transform raw materials into really valuable products, but on a massive industrial scale. Like we said, it is definitely not just mixing chemicals. It's the ultimate science of scale-up. You're taking a tiny laboratory reaction and blowing it up into a 100,000-barrel-a-day reality. And in that reality, literally every single joule of energy and every atom has to be strictly accounted for. All right, Section 1, Molecules to Global Solutions. Let's see how this plays out in the real world. Look at these real-world examples, because this is where it gets incredibly cool. Over at IIT Kharagpur, students took chemical engineering principles, specifically adsorption, and designed low-cost arsenic water filters. That move brought safe drinking water to over 10,000 people in rural villages. Then you've got Biocon. Process engineers there completely flipped pharmaceutical production on its head by moving to continuous insulin manufacturing. They cut the production time from 6 weeks down to just 10 days. And get this, they dropped costs by 40%. And, on a truly gigantic scale, Reliance engineers designed these incredibly complex fluid transfer systems for crude oil. We're talking systems handling 150,000-ton tankers, which ended up saving over 200 crore rupees every single year. So, it's not just theory, this is how engineers actually tackle massive global challenges. Moving on to Section 2, the four-year curriculum. How do you actually learn to do all this? I'm not gonna lie, the academic crucible here is intense. Year 1 is your foundation. You should expect heavy, and I mean heavy, calculus, physics, and basic chemistry. By year 2, the specialization really kicks in. You'll take this infamous class called Material and Energy Balances. It teaches you to track every single atom and every joule of energy moving through a system. Year 3, that's the deep dive. You're hitting reaction engineering, heat and mass transfer, and process control. You basically learn how to keep highly volatile reactions perfectly stable so things don't, blow up. Finally, year 4 brings plant design and a massive capstone project where you literally design an entire, economically viable chemical plant from scratch. To make it through that curriculum, you've got to master both the digital and the physical worlds. On the digital side, you'll be running industry-standard simulation software like Aspen Plus alongside Python and MATLAB. You'll use those to model entirely virtual chemical plants before a single pipe ever gets laid. But then, you also have to truly understand the massive, multi-story industrial hardware. We're talking huge reactors, towering distillation columns, and massive heat exchangers. You have to be able to bridge that gap between a neat little computer model and a 3-story tall piece of hot, pressurized metal. All right, let's hit Section 3, Careers, Salaries, and the Reality of the Job. Let me tell you, a day in the life of a process engineer on a plant floor is incredibly high stakes. In the morning, you might be parsing through thousands of data points from the plant's distributed control system. By the afternoon, you're running debottlenecking simulations, trying to figure out how to safely squeeze 15% more capacity out of a distillation column. Or you're sitting in on intense HAZOP safety studies, basically predicting every single possible way a system could fail. And why is the pressure so high? Well, imagine troubleshooting a tripped distillation column where every hour of downtime literally costs 50 lakh rupees. Yeah. Every single decision you make has massive financial and safety consequences. But hey, the financial reward for taking on all that pressure is pretty substantial. Chemical engineering is consistently one of the highest paying engineering disciplines out there, and the growth trajectory is fantastic. Fresh grads at Tier 1 companies can easily pull in 6 to 10 lakhs per annum. And if you land an elite role at a top tech or pharma company, those numbers jump even higher. By mid-level, you're looking at 10 to 16 lakhs, and senior roles or plant managers can comfortably pull in 18 to 30 lakhs, or honestly, a lot more. Plus, if you look at international opportunities like in the US or the Middle East, those figures can scale up exponentially. Now, we need some radical transparency here. To get to those top-tier salaries, your early career is probably going to demand some grueling work. We are talking about 24/7 rotating shift schedules at hazardous plants. And because refineries and massive chemical complexes require so much space, they're often located in pretty remote industrial zones, far away from those trendy major tech hubs. Oh, and remember all that heavy math from your classes? Yeah, that doesn't go away. Plus, if you end up in the petroleum sector, your career is going to be closely tied to the cyclical booms and busts of the global oil markets. That's just the reality of it. Section 4. The AI and green future. Let's see how this field is adapting. So AI is rapidly transforming the field, absolutely. But here's the thing. It is not replacing the engineer. AI is stepping in to handle the routine monitoring and basic data analysis. Honestly, it can spot a pattern in a failing heat exchanger way faster than a human ever could. But that actually makes the human engineer's true skills so much more valuable. Things like assessing complex safety risks during those haze-up studies, creatively designing completely novel processes from scratch, and managing plant-wide system integration, those remain securely in the hands of the human engineer. Basically, AI is a tool that frees you up to do the really high-level strategic engineering. And right now, a huge chunk of that strategic engineering is totally focused on saving the planet. As the world desperately tries to shift away from fossil fuels, process engineers are standing right at the bleeding edge of the green transition. They're the ones who are going to scale up green hydrogen production. They're designing those incredibly complex carbon capture and storage systems to literally pull CO2 right out of the air. They're engineering massive bioreactors for synthetic biology to create bio-based chemicals. Chemical engineers are the actual people who will build the sustainable infrastructure of tomorrow. Which brings us to our final section. Is this your path? You really have to weigh this out. On one hand, you have incredible versatility, very high pay, and uniquely tangible global impact. But you've got to balance that against the brutally heavy mathematical demands of the coursework, the stark reality of industrial shift work, and the fact that you might be working at some pretty remote plant locations. It's definitely not an easy path, but man, the rewards are profound. If you find yourself deeply fascinated by how things are actually made, if you genuinely love working through complex math to solve physical, real-world puzzles, and if you want to optimize massive systems that have actual life-saving consequences, well, you will absolutely thrive here. The world desperately needs people who can take a tiny beaker of potential and scale it up into a massive global solution. Think about it. The transition to green energy, producing the next generation of medicines, optimizing the basic materials we rely on every single day. It all comes back to this discipline. So the ultimate question is, are you ready to be the engineer that builds tomorrow? Take everything we've talked about, dive a little deeper into the field, and decide if you're up for the challenge. Thanks so much for joining me on this explainer, and I'll catch you next time.